Hidden inside the walls of your house is this incredibly complex web of wires. And there's one set of rules, NEC Article 250, that's pretty much the only thing standing between a totally normal day and a complete electrical disaster. So today, we're going to pull back the curtain and demystify this critical, life-saving safety net. Just picture this for a second. A hot wire comes loose inside your washing machine, and it touches the metal frame. What is the one thing, the only thing, that prevents that entire machine from turning into a massive shock hazard? Well, the answer is in this brilliant, but often misunderstood, system of grounding and bonding. So here's our game plan. We'll start with the mission of this whole system. Then we're going to tackle the huge difference between grounding and bonding. After that, we'll see how your house literally connects to the planet, discover the secret path that trips your breaker in a split second, and wrap it all up with the precise rules that make everything work. Okay, so what is the system's #1 job? You might be surprised to hear it's not about making electricity go. It's about controlling it when it goes wrong. And really, it's that simple and that important. This entire massive article in the electrical code, it all boils down to two things: protecting you and your family from getting shocked and protecting your house from catching fire. Think of it like a dedicated bodyguard for your electrical system, just operating silently in the background 24/7. All right, let's dive into probably the most misunderstood concept in this entire topic. People throw the words grounding and bonding around like they're the same thing. But trust me, in the eyes of the code and, the laws of physics, they have two very different and very specific jobs. Think of it like this. Grounding is your home's connection to the actual earth. It's like a lightning rod for your whole electrical system, designed to handle those huge external threats. Bonding, on the other hand, that's your internal security system. It connects all the metal pipes, the casings, the boxes, all of it together. So if a fault happens, it creates this perfect, clear path for the current to rush back and trip the circuit breaker. And this right here is the official term for that internal security system: low impedance. It's a technical sounding phrase, but all it really means is in super easy path. It's an electrical superhighway. When a fault happens, you want that electricity to have an irresistible, wide-open road right back to the panel so it can trip the breaker in a blink. That's the real magic of bonding. So let's focus on the grounding part of the team for a minute, that physical connection to the Earth itself. I mean, how do you actually connect an entire house to a planet? Well, the code gives us a whole list of approved methods. These are called grounding electrodes. Now, if you happen to have a metal water pipe in the ground or a concrete foundation with rebar in it, that's called a U for ground, the code says you have to use them. They're that good. But for most houses, the method you're going to see almost every time is the good old, simple, and effective driven ground rod. And this is a perfect example of how the code is built for the real world, not just a textbook. What happens when you're hammering an 8-foot rod into the ground and, bam, you hit solid bedrock 2 feet down? The code doesn't just say, oh well, too bad. It gives you options. First, try driving it at an angle. If that's a no-go, you can actually bury it horizontally. The point is, it's all about making sure you get that full 8 feet of metal in contact with the earth one way or another. Now, here's another key rule that explains something you see all the time. The code says that connection to the earth has to be a good connection with 25 ohms of resistance or less. The problem is, measuring that requires expensive, specialized equipment most electricians just don't carry. So the code gives a simple workaround. If you can't prove it's under 25 ohms, just install a second ground rod. And that's why it's become standard practice pretty much everywhere. Okay, so we've anchored our system to the earth to protect it from something like lightning. But now let's talk about the danger you're much more likely to face: an internal fault. And this is where bonding steps up to be your true first line of defense. Get ready for this, because this is probably the biggest aha moment in all of Article 250. We spend all this time and effort connecting our system to the earth, but the code itself says the earth is a terrible path for clearing a fault. A stray current from a faulty appliance isn't going to travel through the dirt and back to the utility pole to trip your breaker. Why? The resistance is just way too high. So here's the crucial takeaway. That ground connection is for lightning and other massive external surges, not for everyday faults. For those, you need that low impedance metal path, the green wire and the metal conduit system we call bonding. It's a direct, clear highway for that fault current to zip back to the panel and slam the breaker open. Relying on the earth for that job just doesn't work.
So we've established we have these two distinct systems. And for them to actually work when you need them most, every single component has to be exactly the right size and installed perfectly. This is absolutely not the place for guesswork.
So, does one size safety wire fit all? Can you just grab any green wire and call it a day? Absolutely not. Not even close. The size of that bonding wire is precisely calculated based on the specific job it has to do. Let's look at two totally different examples. First up, we've got the equipment grounding conductor, or EGC. That's the fancy name for the green or bare copper wire running along with your normal circuit wires to an outlet. And if you look at the chart, its size is based entirely on the circuit breaker that's protecting that circuit. A 20-amp circuit needs a #12 wire because its only job is to carry enough current to trip that specific 20-amp breaker. Simple. But now check this out. This is the main bonding jumper, which is the critical link inside your main panel. Notice how it's not sized by a breaker at all. It's sized based on the massive service wires coming into your house. Wires so big they're measured in units like kcm. And why is that? Because if there's a major fault right there at the service, there is no little breaker to trip. That wire has to be beefy enough to safely carry thousands of amps until the utility company's main fuse blows. And that's the beautiful, simple logic of the code right there. A small wire for a small circuit and a huge wire for the main service. The size of the safety wire is always proportional to the size of the potential disaster it needs to stop. It's really elegant and incredibly effective. And beyond just sizing, there are some non-negotiable golden rules. First, the neutral and ground systems can only be connected at one single spot, your main service panel. That's it. Second, any connections you make have to be on clean, bare metal, not paint, to get a solid connection. And finally, never, ever use flimsy sheet metal screws for these vital connections. They just can't handle the massive fault currents. And hey, here's a little pro tip for you. That concrete encased electrode we mentioned, the U for ground, it's often considered the gold standard of grounding. It uses all that rebar in your foundation to create this massive surface area with the earth. But here's the catch. The connection has to be made before the concrete gets poured. It's a one-shot deal to get the best ground your house can possibly have. So we've pulled back the curtain on this silent, invisible system that keeps you safe every single day. It's this beautiful dance between grounding for the big external threats and bonding for the more common internal faults. The next time you see a green wire or a ground rod, you'll know it's not just some extra piece of hardware. It's a critical part of a life-saving system. So does knowing the why behind these rules change how you look at the wiring in your own home? It probably should.